well, close to the key, and let's see, did pretty well on the first page. Number 3, probably one of the ones people have the most trouble with. And it was number 3 was a rearrangement, trying to make a previous quiz question a little more clear as to what I was asking for in terms of, okay, here's the evidence I want you to consider. Is this consistent, or explain how it is consistent with reaction-driven fracturing and or inconsistent with other mechanisms such as spallation or frost cracking. So just to run through those briefly, depths of soil cover, climate, P-wave velocities, tensile strengths, and elemental transfer coefficients. In terms of depths of soil cover, essentially you're under about 8 meters of soil at one site, and the caption says under 1 meter. Picture is a core stone following excavation of at least 1 meter overburden. So you know that you've got at least 1 meter of soil cover in both cases. In one case, 8 meters. Rules out things like spallation, frost cracking. Climate, you've got plenty of water. That's consistent with reaction-driven weathering. And I only cited the climate in the case, gave the climate information because I only had it for the Sri Lanka case in figure 2. And what was, 16 degrees C mean annual temperature, especially under 8 meters of soil, inconsistent with frost cracking as a mechanism. For P-wave velocities, the little inset graph in figure 1, it's stacked above a graph of tensile strength. And what it's showing you is that there is a peak in the P-wave velocities in the so-called brown band. And so the way that is consistent with reaction-driven weathering, reaction-driven fracturing, that, okay, if in the weathered exterior of the core stone you've got precipitation of minerals, of weathering products filling the pore spaces, then you would expect the P-wave velocities to drop because you're replacing void with rock. And so indeed you do see that peak in the P-wave velocities in that weathered exterior of the core stone. That's consistent with reaction-driven weathering. The tensile strengths, you would expect that while in that same weathered exterior of the core stone that you're precipitating these weathering products, for example calcite, that you're also driving microfracturing, which while you're filling void spaces and increasing P-wave velocities, you're actually decreasing the tensile strength. You're weakening the rock through the microfracturing. So you'd expect that drop in the tensile strength in that same spot, and that is indeed what you see. In terms of the elemental transfer coefficients, you say, well, if I'm precipitating stuff like calcite, then I should either be enriched or at least not depleted of calcium in that weathered exterior of the core stone specifically. And again, where in both figures 1 and 2, in the brown bands, zone 3 in figure 2 and simply labeled brown band in figure 1, you see there is actually a slight elevation in calcium in both cases, although it may be that it's within the bounds of the uncertainty, but at least we can't say with a whole lot of certainty that it's actually enriched in calcium, but at least it's not depleted in calcium. And again, that's consistent with reaction-driven weathering and the precipitation of those weathering products such as calcite in the rock driving that fraction. It's all my design to try to get you actually thinking like scientists and thinking, okay, if this is my hypothesis, what does that hypothesis predict, and does the evidence support, is the evidence consistent with the prediction of the hypothesis? Okay. Let's see, we talked internal ice deformation, yield strength. Still a few issues with people generally got most people got how the existence of an effective yield strength limits or controls ice thickness. And I think again also most people got that what determines the yield strength is that it is a material property that is dependent on the properties of the ice, which are largely determined by temperature and somewhat by pressure. That is, how close are you to the pressure melting point determines the yield strength of the ice. Glacier sliding, meltwater driving pore pressures at the bottom of the ice, allowing the ice to scoot over and up over bumps, leading to cavitation. When the cavities get big enough and there's enough melt, those cavities linking up, draining the water and dropping the pressures, and the surge in sliding stopping at that point. Concomitantly, as you depressurize the cavity and the entire weight of the ice rests on the top of the bump, you create a huge stress gradient between that top of the bump where the weight of the ice is sitting and that atmospheric pressure in the voided cavity on the lee side of the bump. That stress gradient creates or promotes cracking in the rock and coring. 6A, I was really after the most simple form of the erosion deposition equation, simply that the one that's just dz dt equals kappa times d squared z dx squared. That is, that the erosion or deposition rate is proportional to the topographic curvature, and the constant of proportionality is the diffusivity kappa. If you can explain that equation to me, then part B should be straightforward, because you'd say, okay, well, if erosion rate is proportional to the negative curvature, that is the convexity, the magnitude of the curvature, and I see these sharp ridges on one side of the divide and the broad, dull, smooth ridges on the other side, the equation that I gave for part A is telling me that the erosion rate should be greater where those ridges are sharp. It is not necessarily true that erosion rate is greater where slopes are steeper. It may be true, but it is not necessarily true. It is essentially necessarily true based on simple mass balance that high negative curvature gives you a high erosion rate. Okay, number 7 was frost creep. I think did generally well on the first part. The second part, we derived an expression for the diffusivity due to frost creep in class, where we said, well, it's proportional to the strain upon freezing, the square of the freezing depth, and the frequency of freeze thaw. So that's the simple answer to that part. There are other things such as, well, okay, more soil moisture is probably going to contribute to strain upon freezing, and could also get into details of the pore sizes and the grain sizes, but that's all a little bit squishier. Also, though, and I think at least 1 or 2 people mentioned that if the thawing is particularly rapid, then that will lead to increased movement during this sort of gelifluction phase of of the melting, in which you've got water trapped, that melted water trapped above the frozen ground, and it saturates the material, and it sort of oozes. And that's called geliflection or soliflection. Any questions? Okay. So, let me just hand back to you. Go see some other folks up here. Page here, Tara,
Yeah.
Brandon. Okay. Today, I want to talk about water in the landscape. I want to talk about runoff, and I want to talk about channel networks. So, last time we talked about how to generate the pore pressure that's necessary for instability, that is landsliding. And I said contributing area and local rainfall, and that the contributing area helped explain the where of the landsliding, and that the local rainfall helped explain the when of landsliding. Now with those words, contributing area, I kind of snuck in this concept of the drainage basin, otherwise known as the watershed, the catchment. Anybody think of any others? Okay. Essentially what if I'm standing here, what's the area that is contributing flow to this point? What's the area that's uphill, and if I follow steepest descent, of course right now I'm standing on a linoleum floor, so there really is no upslope area, but if I were. Okay, so the drainage basin is both a tool and a result for geomorphic agents, right? It's for geomorphic agents that employ water gathered from upslope, that is. So the fact that much of the landscape is apparently organized to focus water through a narrower space as we go downstream ensures that the water applied to large areas as rainfall is available as focused, rapidly flowing water to our fluvial geomorphic agents trying to rip away at the rock in the stream. It's also true that the result of focusing any stream power is to further carve a notch deeper and thereby draw more water to that spot. So the earth material is shaped and molded to aid in its own destruction, if you will. It's a positive feedback. So one question that is worth considering is, of course, well, what does put the brakes on that positive feedback? If the notching leads to more notching, as if I start with a planar slope and I start notching it, well, that's going to draw more water and further notching and so on. What keeps that from notching all the way down to the level of individual molecules? I'll show you a little animation that I whipped up to help illustrate the point. One of the benefits of computers is that we can simulate geologic time if the rules are simple enough. And turns out we can make a landscape like this out of relatively simple rules. So we start with a plane that's slightly inclined, and there's an inlet at the top that gives us sort of a dominant stream going through the middle of it. And then we turn on uplift, and we can see that the streams start to notch in, especially that big one through the middle. And what we're going to see is that what we're going to see is that as that big stream notches down, the other streams are going to notch down, but they're going to reorganize themselves to drain towards the big one. In general, flow is going to try to take the path of steepest descent, and given enough time, a landscape will tend to organize itself such that landscapes don't try to do anything, but it will, in general, organize itself such that water will take something like the shortest path to the lowest level. Is there a question in the back?
Yeah, the main factor driving uplift in this area is the far field tectonics, or just removal of mass.
Oh, it's just a number. It's just a parameter. So that's the thing about this model. So yeah, uplift is simply the same everywhere except at the boundary. At the boundary it's 0, here it's some positive number. So we're putting in material, we're essentially jacking up the whole thing by small increments every iteration, and then leaving the processes, which are simply the carving due to fluvial processes, the accumulation of flow, so depending on contributing area, and but the other thing that you will probably notice is that not all of the landscape is channeled, right? That there are still somewhat rounded slopes between the channels, that while the channel network fills the entire two-dimensional space, more or less, most of the pixels in that landscape are actually on the slopes, right? That the channel network actually is the water's focused into those channels, and they take up very small amounts of the total area, relatively small amounts of the total area. So we do have that finite spacing between channels, which leads me to my first major thing, if you will. Ben the nubs. Little thing called drainage density. A lot of our perception of a landscape is based on its drainage density. How finely is that landscape dissected by streams versus how undissected is it? Are we in a place like the Coast Range where there's streams every 100 meters? Or are we in a place like the High Cascades where you can wander around for a while without encountering a stream? I tend to get lost without a compass in the High Cascades because of that. So, so what's drainage density? We'll give it a handy little double D symbol, not for daredevil, but for drainage density. And it is the integrated length of channels divided by the total area of the drainage basin. So, in order to get at this point, it's worth a bit of conceptual build-up, I think. So, we can conceptually and practically organize the channel network as a set of so-called links. Let me just draw what I mean by that. If I just make what every hydrologist will draw for a standard leaf-shaped drainage basin, I've got some channels. And they should all meet up. I can define, so if this whole thing has an area total drainage basin area, and then we can say, well, let's say take this here, we'll call that a so-called interior length. And it's defined by a confluence on its upstream end and its confluence with another stream on the downstream end. So these interior links are simply defined, are all these things that are defined by confluences at their ends. Okay? And this is just a handy way of organizing things. We can also define an exterior link because not all of our pieces of channel have confluences on both ends. Some of them have their upstream end as the channel head. And so the exterior links are those that are defined by the channel head at the upstream end and a confluence at the downstream end. Any of these links, we can measure its properties, and in particular, we can measure its length. So this one here, we'll call that link I, and it has a length L sub I. Okay, L for length, not too complicated. If I have, so I wanted, the main reason I wanted to throw this up here is that so I can write down an expression for the integrated length of all the channels. And so that integrated length is just, say total length is simply the sum from I equals 1 to n. If we have n links, it's the sum of all the lengths of the individual links. And then I can write drainage density as the ratio of that sum over the total basin area. Okay. Now we can immediately notice one thing about this. Its units are a bit odd, I suppose. It has units of inverse length. This L not to be confused with the measurement L, it's just meaning length, dimensions. So it has dimensions of inverse length. And that length, we might suppose, is, since this is a drainage density, it's describing this texture of the landscape. Oh boy, the animation has gone away. That the drainage density is going to be similar to the inverse of the length between, or the distance between channels. It's not exactly that. I can't write an exact expression saying that, but it's gonna, those numbers are going to be similar magnitude. So if we wanted to get a rough order of magnitude of the drainage density, we could go to sort of a typical spacing between channels, measure that distance, invert it, and that would give us, again, a number similar magnitude as the drainage density. So a high drainage density means a small distance between channels. A small drainage density means a large distance between channels. So some place like the Oregon Coast Range has a high drainage density. Some place like the High Cascades generally has a low drainage density. Long distance between channels, get lost without a compass. Okay. Or GPS nowadays. Nobody gets lost anymore. Unless your battery dies. So recall, if you will, let me pull up. So recall, if you will, Chip Ross Park. Because the question I want to pose is, well, what sets the drainage density? I've told you how you can calculate it, but what actually determines that channel spacing? Let me see. Here's my Oregon Coast Range oblique aerial photo, high drainage density landscape. But here's Chip Ross Park. Not on the day we were there. This is oh, it reminds me of how many years ago this would have been because of how small my children are. But this is, I think I may have shown you these pictures. I've at least told you that I had them. That is actual photographic evidence of water flowing at the bottoms of these ravines. I think probably that slope there is the one that we were all clambering all over. And boy, I don't see any gopher mounds in this picture. But, all right, so I'm trying to get at what determines the channel spacing. If there were never any water flowing down there, what would happen? Yeah, exactly. It would. I mean, it totally would, right? All those gophers would still be digging away. I mean, we're assuming that fundamentally the climate doesn't change and they don't, you know, die of thirst or anything right away. But if there were never any water flowing there, the gophers would fill it in. They would at least, you know, start to, you would see the tips of that ravine, the tips of that notch start to get filled in. Especially, say we just decreased dramatically the frequency of water flowing down here, you would start to see the gophers fill in those places that are at the extremes tips of the ravine or drainage network. Conversely, what if the gophers all suddenly went extinct? What would happen to the slopes?
When it just like becomes steeper, essentially, like you get a really
you get a deep channel, but what would happen to the slope itself? I mean, if say you steepen it here, what would be the next thing? You'd start to get gullying up into that slope, right? The gullies would start tearing that slope apart. And if there were absolutely no mechanism for smoothing and filling in those gullies, eventually it would all be gully. And that's, you know, we have a name for that. It's called badlands. So without the gophers smoothing things out, this would probably progress to badlands, or it'd probably progress to a bedrock landscape. I don't know. The grass would have to die too. These are some sort of badlands. Chip Ross seems to be pretty much, gophers and flowing water, kind of copacetic. They've kind of reached the standoff. This is a place called Bijou Creek in Colorado, east of Denver, and here you've got a farm up on that upland, and this area between the farm and the creek, that way, just getting torn apart by this gully network. So this is, I don't know if what happened to the gophers here. I mean, they're not doing their thing, I guess, or maybe it's all about vegetation. So each slope, each of those things, a slope and a ravine or a gully, exists because the process that forms it is not overwhelmed by the process forming the other. So the rounded slope remains a rounded slope because the gophers bury any incipient gullies that would otherwise tear it apart. The notched ravine remains notched because the flowing water carries away any attempt by the gophers to fill it up. So drainage density is determined by that competition between, in the case of Chip Ross, between the flowing water and the gophers. Between those processes that tend to notch and cut versus those processes that tend to smooth things out and fill stuff in. Now, in the animation I showed you, maybe I can find it again. In the animation, that's that competition, or the relative magnitude of those two processes, the diffusive processes that tend to smooth things out, fill stuff in, nice goggles even, and the processes that notch in are simply set by parameters in the model. Literally I'm running a numerical diffusion equation on the entire landscape. The magnitude of that diffusivity in that equation determines where diffusion is enough to outcompete the fluvial processes that are trying to cut the landscape apart into channels. Now, in order to do any of that fluvial work in reality, what do we need? Well, we need some flowing water, right? So the question is, how do we get the flowing water? Well, rain, duh. Okay, yeah, duh, rain. Let's pose it this way. How do we get enough water to flow over the surface rather than soak into the ground? Well, generally we can talk of overland flow. There's water flowing over the surface of at least a couple of types. A couple being two that I will discuss. Okay? So, the first is known as, okay, that's not happening for me. The first occurs when the rate of rainfall exceeds the infiltration, the maximum possible precipitation rate in the soil. And it's named after a guy, Robert Horton. So often, because infiltration excess overland flow is just, it's 4 words instead of 3, we often shorthand it as Horton overland flow, or HOF for short. Again, this is just that rainfall so we'll call the rainfall rate P for precipitation, that the rainfall rate exceeds the infiltration capacity, sometimes referred to writing with something like my thumb. So what is KSAT? KSAT is a stand-in, and we'll talk about it more, so don't panic, because I'm going to talk about KSAT quite a bit. But that's simply standing in for something known as the saturated hydraulic conductivity. That is once the ground is good and wet and the water is soaking in and we no longer have the sort of surface tension actually sucking the water in, we've got some rate at which the water can seep into unsaturated soil. And if the rainfall rate exceeds that, then we'll get overland flow. Around here, where do we see this? Like in Western Oregon, really. Roofs, parking lots, streets, okay, asphalt, anything paved or covered with glass and metal, roof of your car, you're going to get some infiltration excess overland flow, at least you hope, right? If your roof, you hope your roof has a very small infiltration capacity, namely 0, right? Okay, well, if we don't get any of that around here, I mean that, typically you have to have really strong rainfall and relatively impermeable ground in order to get Horton overland flow. Badlands come to mind again. The second sort, then, is known as saturation overland flow. SOF for short. Sometimes referred to as Dunn flow, after Thomas Dunn. But he's still alive, and so I don't really feel like we should name it after him just yet. So saturation overland flow occurs when the ground is fully saturated. There's no more room for infiltration. The water table has reached the surface. So let's just draw ourselves a bit of a picture to start. So I've got a slope and a water table. Well, I've got rainfall. Got my ground surface. And I've got a water table which might at some point actually intersect the surface. There's the difference in slope between the water table and the surface drawn here is greatly exaggerated. But let's go ahead and draw up here that we've got some slope angle theta. And at this point is where we get saturation overland flow. Now, the next thing I want to ask then is, what's the discharge at that point? What's the discharge where we've got saturation overland flow? Let's make a couple of symbols. So my rainfall rate again is P. I've got some upslope contributing area. Call it capital A. Well, so that A, that is upslope of that point. Well, we got a couple of ways to figure out what the discharge is. We have discharge capital Q as units of volume or length cubed per time. So let's see. Let's just look at some units real quick. Precipitation rate, that's a length per time. Contributing area, that's a length squared. So what's one way, just simple conservation of mass, to figure out, and let me say, it's raining this hard, and it has been raining this hard forever. At least, in Oregon. Not yet, pretend it's, end of November instead of beginning. Well, simple conservation of mass says that my discharge is equal to the precipitation rate times the contributing area. I mean, those are the only two things I drew the units up for and put them together and I get the right units. Makes sense too. I mean, it's the rainfall rate falling on this area. Okay, if that's all focused through this point, then that has to be the discharge. All right, so we get one expression for contributing or for discharge from simple conservation of mass. Anybody think of another way we might figure it out? Well, at least right at this point, all the water is still flowing in the subsurface. So anybody know anything about groundwater? Anybody know a little thing called Darcy's law? Who's Darcy? Who cares? He came up with this law. I don't know Darcy. I've never known Darcy. Tom Dunn, so I'm protected with him. But all right. So from Darcy's law, it says that discharge is what? Discharge, well, Darcy's law says that the volumetric flow rate, which has units of length per time, it's not actually a velocity, but it just has units of velocity. Volumetric flow rate is proportional to the head gradient. What's the head gradient? It's the slope of the water table. And that constant of proportionality is this thing called hydraulic conductivity or saturated hydraulic conductivity or KSAT that I just erased. Okay, so this, if I'm trying to get discharge okay, so let's one thing at a time. So the volumetric flow rate is, my sat conductivity times the head gradient. And in order to get discharge, that is length cubed per time, if this is going to give me length per time, I need area. What's the relevant area in this case? I haven't labeled it or anything, but it's whatever cross-section that stuff's flowing through. That stuff being the water in the subsurface. All right, let's let me draw a different look. That's not what I want. So now imagine I've got a contributing area that is focusing flow down here. I've got a contour width. For the width of my cross section, right there. I've got a soil thickness. I'll stick with our big H. And I'm out of time. But it's that H times W that's going to give us our cross-sectional area. And we'll go from there next time. While you're moving around, packing up, I'll tell you, well, we can, if we've got two equations, if there's something we don't know, we can solve for it. So if we want to know, for example, the contributing area per contour width at which we would get saturation overland flow at this precipitation rate, we can solve for it. The other thing to note is that if I draw a water table in here, that's starting to look an awful lot like our landsliding case. And this is how we might solve for how much pore pressure we've got. All right, see you all next time.